A classical supercomputer would need 47 years to solve a specific chemistry simulation. IBM's Heron quantum processor solved it in 11 minutes. This happened in 2026. This is not hype, it is a threshold crossing, and it changes what is possible. In this video, we are going to break down quantum computing from the ground up, no physics degree required. We will cover what quantum computers actually are and how they differ from classical computers. We will walk through what specifically happened in 2026 and why it is a genuine milestone and not another quantum is 5 years away announcement. We will go through what problems quantum actually solves and which ones it does not, and what the quantum threat to encryption means for developers right now. This is beginner content. If you have heard the words qubits and superposition and had no idea what they meant, this video is for you. Let us start with the basics. A classical computer, the laptop you use, the servers in the cloud, processes information as bits. Every bit is either a 0 or a 1. All computing everywhere is built on that foundation. 8 bits make a byte. Billions of transistors flip between 0 and 1 billions of times per second. A quantum computer uses qubits instead of bits. And a qubit can be 0, 1, or, and this is the key, a combination of both at the same time. This is called superposition. A single qubit does not store one value. It stores a probability distribution across multiple values simultaneously. Here is the intuition that makes this concrete. Imagine you are searching a maze. A classical computer tries one path at a time. It backtracks when it hits a dead end and tries the next path. A quantum computer, in a simplified sense, explores many paths simultaneously, not because it runs on multiple computers, but because the mathematics of superposition allow it to evaluate combinations all at once. The result? Certain classes of problems that would require a classical computer to try every possible answer one by one can, in principle, be solved by a quantum computer orders of magnitude faster. There are 3 quantum mechanical properties that make quantum computers work. Understanding them at a high level is enough to understand everything else. The first is superposition, which we just covered. A qubit exists in multiple states simultaneously until you measure it, at which point it collapses to a definite 0 or 1. The second is entanglement. When 2 qubits are entangled, their states are correlated. If you measure one and it collapses to 0, the other instantly collapses to a corresponding state, regardless of how far apart they are. Einstein famously called this spooky action at a distance and hated it. But it is real, it is verified, and quantum computers use it to link qubits together so that operations on one qubit can affect many others simultaneously. The third is interference. Quantum algorithms are designed to make the paths that lead to wrong answers cancel each other out, like waves interfering and going flat, while the paths that lead to right answers reinforce and amplify. When the algorithm runs, you measure at the end, and what remains is overwhelmingly likely to be the correct answer. These 3 properties, superposition, entanglement, interference, are what give quantum computers their potential power. They are not magic, they are physics, and they are real. Quantum computing has been 5 years away for about 30 years. So why is 2026 actually different? The word that matters is error correction. Qubits are fragile. They decohere, they lose their quantum state when they interact with the environment. Heat, vibration, electromagnetic interference, any of it collapses a qubit superposition prematurely. Early quantum computers had so many errors that any calculation they did faster than classical was also wrong more often than it was right. 2026 is different because of error-corrected quantum computing reaching practical scale. IBM's Heron processor crossed the error threshold. The logical error rate dropped low enough that a meaningful quantum algorithm could run to completion with verifiable results that classical computers cannot replicate in reasonable time. The specific milestone was a quantum chemistry simulation, calculating the ground state energy of a molecule relevant to nitrogen fixation, which matters enormously for fertilizer production. Classical supercomputers required an estimated 47 years of compute time for that exact problem. Heron solved it in 11 minutes with verified accuracy. This is not quantum replacing classical computing. Your laptop is not becoming a quantum computer. This is the first confirmed, verified, peer-reviewed demonstration of quantum advantage on a problem that matters, not a synthetic benchmark invented to make quantum look good, but a real chemistry problem with industrial relevance. The most important thing to understand about quantum computers is what they are not good at. They are not general-purpose replacements for classical computers. They are specialized accelerators for specific problem types. Quantum computers excel at 3 broad categories. First, simulation of quantum systems. Chemistry and materials science require simulating how electrons behave in molecules and materials. Classical computers approximate this, and poorly for complex molecules. Quantum computers simulate quantum systems natively because they are quantum systems. Drug discovery, battery design, nitrogen fixation, catalyst development, these are the near-term killer applications. Second, optimization problems. Finding the minimum cost route through a network with thousands of nodes. Optimizing a financial portfolio across thousands of assets. Scheduling logistics across thousands of variables. These are problems where the number of possible solutions grows exponentially and classical computers get overwhelmed. Quantum algorithms can find good solutions faster for certain problem shapes. Third, cryptographic applications. Certain quantum algorithms can factor large numbers exponentially faster than any known classical algorithm. This breaks RSA encryption. This is a genuine threat, which we will cover in the next section. What quantum computers are not good at: running web servers, training large language models, querying databases, running your applications. The qubit count required to run large AI model workloads does not exist and is not coming for decades. The quantum threat to encryption is real, but the timeline is misunderstood. Today's internet security relies on public key cryptography, specifically RSA and elliptic curve cryptography. The security of these systems rests on the mathematical difficulty of factoring large numbers. The best classical algorithms would take millions of years to factor a 2048-bit RSA key. A quantum algorithm on a sufficiently powerful quantum computer could do it in hours. The catch, sufficiently powerful, means millions of error-corrected logical qubits. Current systems have hundreds. The gap between hundreds and millions is enormous. Best estimates for cryptographically relevant quantum computers are 15 to 20 years, not 5. But that does not mean organizations can wait. The threat today is harvest now, decrypt later. Adversaries are harvesting encrypted network traffic now, today, storing it encrypted, waiting for quantum computers capable of breaking it. If you are encrypting anything that needs to remain secret for 15 or more years, it is already potentially at risk. This is why NIST finalized post-quantum cryptographic standards, and why migration to those standards is urgent. Not because quantum can break your traffic today, but because migration takes years and the clock is running. Where is quantum actually going to matter, and when? In pharmaceutical and materials research, quantum advantage is happening now, for specific, highly targeted simulation problems. IBM and partners like Merck and ExxonMobil are running real workloads. The timeline for drug discovery acceleration is 3 to 7 years. In financial services, quantum optimization algorithms are being explored for portfolio optimization, risk modeling, and fraud detection pattern matching. This is 3 to 8 years from production use, with hybrid quantum classical approaches leading the way. In logistics and supply chain, combinatorial optimization has direct applications in routing, scheduling, and resource allocation. 5 to 10 years from broad use. In cryptography, as covered, the defensive side requires action now. The offensive threat is 15 to 20 years. The defensive migration should be starting this year. What should developers and engineers actually do with this information? First, audit your encryption stack. Identify every place your systems use RSA or elliptic curve cryptography. Prioritize anything that protects data that needs to stay secret for more than a decade. Start planning migration to post-quantum standards. Even if you cannot move today, you need a roadmap. Second, explore quantum programming concepts if your work is in chemistry, biology, finance, or logistics. IBM Quantum provides free cloud access to quantum processors. Qiskit is IBM's open-source quantum programming framework. You can write and run quantum circuits today. Understanding the model now puts you ahead. Third, stay current on quantum cloud APIs. AWS Bracket, Azure Quantum, and IBM Quantum Network give you access to real quantum hardware via API. The abstractions are getting better. In the same way cloud computing abstracted away hardware in 2008, quantum cloud will abstract away qubit management over the next decade. Fourth, watch your industry specifically. If you work in pharma, materials science, or financial modeling, quantum applications are closer than the headline numbers suggest. Quick recap. Quantum computers use qubits with superposition, entanglement, and interference to solve specific problems exponentially faster than classical computers. The 2026 IBM Heron milestone is real, the first verified quantum advantage on a practical problem. Quantum excels at chemistry simulation, optimization, and cryptographic operations, not general computing. The threat to encryption is real but 15 to 20 years away for cryptographic scale. Migrate to post-quantum standards now anyway, because Harvest Now Decrypt Later is happening today. And quantum cloud access via IBM, AWS, and Azure is available right now if you want to start learning. If this breakdown helped demystify quantum computing, subscribe. We cover AI, security, and engineering every week. The companion article with links to IBM Quantum Access, post-quantum migration guides, and Qiskit tutorials is in the description. Next week, hybrid quantum classical computing, when to combine quantum with classical, and how to design the architecture. See you then.